Hello, students. My name is Mr. Mankata. I'm going to be your teacher this summer for Physics 2 for Proyecto Science. Before we get into the content for today, I think it'd be a good idea to give you an overview of how the class is going to run. For the most part, it's going to start off with a pre-recorded session, just like how this video is pre-recorded, of me explaining the topic of for the day. And then it's going to be followed by a discussion portion where any questions you may have had while watching the pre-recorded session, or any questions in general that you may have of what you watched today, you can bring up. So with that out of the way, I think it'd be good to start off by reviewing some of your Physics 1 topics before we get into Physics 2. So Physics 2 is going to deal a lot with um, momentum, collision, and rotational kinematics. So it'd be a good idea to review these basic concepts that you learn in Physics 1. So we're going to start off by reviewing vectors. Now, a vector, as you may know, is basically a value. Let's say we have a student here and they throw a ball diagonally. This student just threw this ball with a vector. Now, what a vector is, it shows us the direction and motion that an object may have. So, for example, because this ball is being thrown diagonally, we know that we can break this diagonal component into a horizontal and vertical component. Uh, a common example would be if someone throws something, let's draw a coordinate plane. If someone throws something with a vector of magnitude 5, this is a special triangle where this side is equal to 3 and this is equal to 4. It's a 3, 4, 5 triangle. Now, many of these triangles exist, but for the most part, we won't be getting into anything too complicated. It is important for you to know how to recognize vectors. For example, if I say, let's say I give the example, let's say you're at a coordinate plane, and I say, okay, you take 2 steps to the right, 3 steps downward, 2 more steps to the right, and then 1 upward. So this is where you end, this is where you started. You need to be able to tell me, oh, how far from the start are you? Which shouldn't be a problem. I won't give you anything that I don't think you guys can handle, so you don't have to worry about that. But that's basically as much as I'll expect in terms of vectors. Now, the next topic, kinematics, has to deal with motion of objects. So the equations you may have seen would be speed is equal to distance over time, right? So it's important for you guys going forward to understand how to use this equation, because speed and, more importantly, velocity is going to play an important role in momentum in the topics that we're going to be covering in this course. So before we keep going, I'm going to point out what the differences between speed and velocity are. Speed is what we call a scalar, and velocity is a vector. Now, a scalar is any quantity that it does not matter if it's the direction of it does not matter. If if you guys are following. So for example, let's think of time, right? So time. As far as we know, time only moves in one direction, forward. So it doesn't make sense for someone to say, oh, I am -5 seconds late. You just say, oh, I'm 5 seconds late. Because time doesn't have that negative direction to it. And that's what speed is. If I have a car and I'm driving it, let's say 5 miles per hour, you would say, and I ask you, hey, what's my speed? You would say, oh, your speed is 5 miles per hour. If I have that same car, just copy it here. But then instead of going to the right, I'm going to the left. I ask you, hey, what's my speed? You would still say, oh, your speed is 5 miles per hour. But if I ask you, for case one over here, what's my velocity? You say 5 miles per hour to the right. If I ask for case two, what's my velocity? You have to say it's either -5 miles per hour or you say 5 miles per hour to the left. And the reason for this is because with velocity, the direction of it matters. That's what makes it a vector. You know, as we saw over here at the top, vectors depend on the direction. It is not the same to throw a ball in this diagonal than to throw it upward. Like if this is 5 and this is 5, you guys can clearly see that they're not going to the same place. And that's why direction matters for vectors. Now, moving on with kinematics, there's a few important, I would say, values that we need to take into consideration. Some of them we already saw with this equation up here. So the first one's going to be velocity, which our variable for velocity is going to be v. Next, it's going to be distance or displacement. Or displacement. Our variable for this is going to be x. Now, there is also a difference between distance and displacement. Distance has to do with your overall, distance traveled. So like if I tell you, hey, I'm in this coordinate plane and I take 2 steps to the right and then 3 steps to the left and then 3 steps to the left, I end up over here. Now, my distance traveled would be the total distance. So I would say, okay, I moved 1, 2 to the right, and then 3, 4, 5 to the left. So my distance traveled is 5. But your displacement only has to deal with your distance from where you started. So in this case, my displacement is just -1. And this is going to be very important for you guys to understand going forward, the difference between distance and displacement. The easiest way to think of it is displacement is going to be your x final minus your x initial. So what this means is your displacement is always going to be where you are minus where you started. So for example, our x final in this case right here is -1. And our x initial is 0 because we start at the origin. So we have -1 minus 0, -1. So our displacement is -1, as we can see. But for the distance, as we had seen, it's 1, 2, 3, 4, 5. So clearly 5 and -1 are two different values. So we have seen velocity, we have seen distance and displacement. The next one is going to be simply time. And our variable is going to be t. Time is very straightforward. Time, like I said, it's just a scalar, so it can't be negative time or upside down time. It is just a magnitude. It's just always a positive number. Okay. Then we're also going to have acceleration. And our variable for that is going to be a. Now, acceleration is going to be important because it shows us how our object is either speeding up or slowing down. Now, if our velocity is constant, right, our velocity is not changing, let's say our car is always going to move at the same speed. It's always going to be 5 miles per hour. That is when our velocity is constant. But if we introduce an acceleration to the car, maybe when time is equal to 0, our velocity is 5. But then when time is equal to 5, it might be 10 miles per hour. And then let's say at time is equal to 10 seconds, our car has a negative acceleration. It means that it's slowing down. So it might go down to 5 miles per hour again. So it just tells us how the velocity of our car is going to be changing, or how the velocity of our object is going to change. Now, for dynamics, we're going to be dealing with Newton's laws of motion. So, for the sake of this class, you only need to understand the second law of motion. Now, you need to know that all three laws of motions work together to create basically the foundation of the physics that you're learning. So, what the second law of motion tells us is that a force that's applied to an object is going to be equal to the mass of that object times the acceleration of the object. Now, we just saw what acceleration is. Mass has to deal, it's inert property of an object. It's kind of like how they always tell you, oh, you weigh 100 pounds on Earth, but you actually weigh 30 pounds on the moon. Weight can change, but your mass is constant no matter where. And the reason for that is because weight is a value given to you based on the force applied to you by Earth. And we'll get into that a bit later. But for now, it's just important for you guys to understand the basics, the foundational aspects of this equation. So let's say I have a box, say I have a box right here. If I decide that I need to move this box somewhere, I need to apply a force on it going this way. Now, the force that I'm applying on it is going to be right here where there's contact. And the force is going to depend on how hard I hit it and how fast it's going, right? And then depending on how heavy it is, like if I push it really hard and it's very light, I'm going to apply a very big force. But if I push it just as hard and it's very heavy, my force is not going to be as big. Okay? Now, the last topic that we'll slightly go over is going to be energy. And the reason why I say slightly is because energy and momentum are very close hand in hand. So as we go over momentum, we'll be touching up on topics on energy. That way that you guys get a better grasp for the content. Now, what is energy? Energy can be found in three different ways in kinematics in the physics that we're going to be doing. There's going to be gravitational potential energy. I'm going to label it U sub G. So that's gravitational potential energy. We're going to have kinetic energy. And lastly, we're going to have elastic potential energy. So these are the three types of energies that we would see in the type of physics that we're going to be doing. So let's start off with gravitational potential energy. This type of energy is present whenever an object is basically not touching the floor. So for example, let's say we have a seesaw, just like this. And we have one student over here and one student over here. Now, if this is the floor, we can clearly see that student 1 over here is touching the floor while student 2 is high up in the air. Now, if I ask you which student has the greater gravitational potential energy, your answer should be student number 2. Why? Because student number 2 is not even touching the floor. It's off the ground. And that is when gravitational potential energy is present. Student 1 is right at the floor, so it's experiencing no gravitational potential energy. Okay. Now for kinetic energy, this one's really straightforward. Kinetic energy is always present when there is a velocity tied to an object that has mass. So just anything will do, just for consistency. Let's say our car. Let's say our car weighs 1,000 kilograms. Okay, and then it's moving 50 miles per hour. That's going to be its velocity, 50 miles per hour to the right. Then I would say, yeah, this car has kinetic energy. Why? It has mass and it has a velocity. And those are the two criteria that you need in order to have kinetic energy. And the last one, elastic potential energy, is the one that we might see the least, but nevertheless, I'm gonna slightly touch up on it. Is basically whenever you have a spring. So let's say this is a wall, there's a spring, and you have an object attached to it. Whenever the object is like oscillating, so it's like here now, but then it's like compressed, so now it's here, and then it's gonna like stretch out, so now it's all the way here. As it's doing this compressing and expanding, it's gonna have different elastic potential energy. Now, all three of these energies have their own equations that go with them. Again, we'll start off with gravitational potential energy. The equation that goes with gravitational potential energy is mgh, where m is the mass of the object as we've seen, h is the distance off the ground, and g is the acceleration due to gravity. Now, near the surface of the Earth, the value for g is 9.8 meters per second squared. And this value holds true for all of the problems that we're going to be doing in this class. Okay? Now for kinetic energy, our equation is K is equal to 1/2 mv squared, where m is going to be our mass and v is our velocity. Okay, pretty straightforward. And lastly, our elastic potential energies equation is 1/2 k x squared, where x is going to be the distance that the spring is stretched. So for example, this is one x, this is a different x, this is a different x. And our k value is actually gonna depend on the actual material of the spring. So different springs have different k values, even if they're like the same, size and weight and stuff like that. Okay. Now, lastly, just to be thorough, it is very important that you guys understand the value of units. So units, very important. So in this class and all the physics classes that you might see going forward, we use SI units. So what does this mean? When we're talking about meters, this has to deal with our distance or displacement. When we're talking about seconds, that has to deal with T for time. And when we're talking about, for example, meters per second, this is velocity. Meters per second squared is acceleration. Now, you might see that this is the same as this unit right here. And of course it is, because gravity is an acceleration. You accelerate downward. It's like if you jump up, gravity accelerates you back downward. Okay? And lastly, we're going to have, well, not lastly, first we have newtons. It's just capital N. Newtons. And this is the unit for force. And lastly, we have the joule. This is going to be our unit for energy. Okay? So the reason why SI units are so important is because you've heard, for example, of kilometers or millimeters or milliseconds, and these values are very important because it allows you to express big numbers in very condensedly, because you're able to interchange units like that. So for example, if I say 1,000 meters is the same as saying 1 kilometer. Okay? And in future lessons, we're gonna, as we're doing our problems, you might see a problem that uses minutes instead of seconds, or it might use kilometer instead of meters. And you're gonna be able to switch between units, so you can go from kilometer to meter, and then also be able to solve problems that have different units than the ones that you're used to. But for this review, I think this concludes it. We're now gonna head into our discussion portion of the class. Uh, Please feel free to ask any questions. Do not be shy. I am here to help you. And yeah, I'm really looking forward to teaching you guys this summer.